Imagine a laptop you charge once a week that operates 10 times faster than the device you're watching this on. To understand how we get there, we have to look at the engine of our modern technological world, silicon. We have pushed silicon to its absolute physical limit. If engineers try to make silicon transistors any smaller or faster, the material overheats and physically degrades. For over a decade, the anticipated replacement has been graphene, a wonder material made of a single layer of carbon atoms. Graphene is a perfect conductor of electricity, allowing energy to move through it with almost zero resistance. But processing information requires binary code. Electricity flowing registers a 1, and stopping registers a 0. Because graphene is such a perfect conductor, it acts as a perpetual 1. It has no natural off switch. If you cannot stop the flow of electricity, you cannot process data. No matter how fast it conducts, without a 0, pure graphene cannot function in a circuit. A functional semiconductor must act as both a conductor to let energy pass and as an insulator to block it, entirely on command. To achieve this, materials need a property called a band gap. Think of a band gap as a microscopic energy chasm electrons must be forced to cross. Silicon has a natural band gap. Engineers control voltage to make electrons jump the chasm or stop them in their tracks. Pure graphene has 0 band gap. The chasm doesn't exist, so the flow of electricity cannot be controlled. For 10 years, material scientists globally tried to force a band gap into graphene, and for 10 years, the material refused to cooperate. That was the status quo until a research team at the Georgia Institute of Technology decided to tackle this specific physical puzzle. Successfully creating a band gap in graphene removes the primary physical barrier to the next leap in computing power. The Georgia Tech team achieved this through a process called band gap engineering. This involves manipulating the material precisely at the atomic level. By growing graphene on specifically treated silicon carbide wafers, the researchers physically squeezed and warped the carbon lattice. This strain forced a microscopic chasm to open where none existed naturally. When they tested this warped structure, the endless flow of electricity through the graphene was abruptly halted. What you are looking at here is the physical proof. This is a test wafer of these newly engineered chips resting on dark foam. By successfully engineering an off switch, they finally forced that perpetual 1 to become a 0. After a decade of research, the team had turned a raw, highly conductive material into the world's first functional graphene semiconductor. Now that the underlying physics problem is solved, the industry can focus on manufacturing these wafers at scale using existing production machinery. Because electricity moves through this engineered graphene with almost 0 resistance, it eliminates the massive heat generation that stalled silicon's progress. This physical shift signals the transition from the gigahertz age into the terahertz era. A terahertz is 1 trillion cycles per second, a 1,000-fold increase over the speeds we've been stuck at for decades. Those week-long batteries and exponentially faster laptops are no longer just science fiction. They are physically achievable. The physical limit that held silicon back for years has been broken. The next leap in computing rests on a single atomic layer of carbon and the ability to finally make it pause.